Hi everyone, welcome to my channel. Today, let's talk about the topic of contrasting metallic and carbonic surfaces in olefin hydrogenation provides insights on the origin of the pairwise hydrogen addition. The perohydrogen-induced polarization was always used in olefin hydrogenation to analyze that how much percent goes to the pairwise addition. Generally, the non-pairwise involve the addition of the ortho hydrogen and the pairwise is the perohydrogen. In principle, the non-pairwise addition represents the rapid hydrogen diffusion and the pairwise addition represents the slow hydrogen diffusion. So how does the relationship between the hydrogen diffusion rate, hydrogenation pathway, and the contribution of the pairwise addition? And here are the models we use in this study, including the different stacking of the molybdenum carbide MXene, ABA and ABC, as well the rhodium. In addition, the strong absorption gypsy-free energy of the reactants hydrogen and ethene, as well the weak absorption gypsy-free energy of the product ethene, were first used to evaluate the preliminary feasibility of the olefin hydrogenation. And please note here is the gypsy-free energy. And then we use the electronic energy to estimate the absorption and the desorption rate as a function of the pressure and the temperature, showing that the reactants hydrogen and the ethene can absorb easily, even though the ethene is slightly stronger, and the product ethene can dissolve easily when it was generated. So this is a favorable feature for catalyst performance. And then the optimal absorption sites of the reactants hydrogen and the ethene were first identified, followed by the analysis of the hydrogen dissociation, and finally the ABA molybdenum carbide 1B, ABC molybdenum carbide 1C, and the rhodium 2B were selected for further investigation of the hydrogenation pathways. Here are the different hydrogenation pathways we designed. But before proceeding these pathways, we first studied the Ely radio mechanism because it only considered the pairwise addition. But due to their high energy barrier, this mechanism was first ruled out. Here are the hydrogenation pathways on clean hydrogen coverage and ethene coverage surfaces using the span energy barrier, which is the energy difference between the transition state with the highest energy and the intermediate with the lowest energy. And for the ABA molybdenum carbide, comparing with the clean surface, the hydrogen coverage decreases the reaction energy barrier and increases the hydrogen diffusion energy barrier. However, for the ethene coverage, it increases the reaction energy barrier, maybe due to the choice of configuration, and it also has a very limited effect on the hydrogen diffusion energy barrier. Next, for the ABC molybdenum carbide, still comparing with the clean surface, the both hydrogen and ethene coverage decrease the reaction energy barrier, and the hydrogen coverage still increase the hydrogen diffusion energy barrier. The ethene coverage still has a very limited effect on the hydrogen diffusion energy barrier. And then for the rhodium, regardless of the coverage, the decrease or increase in the energy barrier is less significant than that of the molybdenum carbide ABA and the molybdenum carbide ABC. So these results indicate that the surface coverage effectively reduces the hydrogenation reaction energy barriers and increases the hydrogen diffusion energy barriers. And then the ratio of the hydrogen diffusion rate to the hydrogenation reaction rate indicates that pairwise is not favorable. But the percent of the pairwise for rhodium is always higher than that of the molybdenum carbide. So we conclude that the dynamic site blocking due to high adsorbate coverage or other mechanisms may significantly restrict the hydrogen diffusion and further enhance the pairwise hydrogenation. And finally, thanks for all the institutions and the organizations that support this work. And also, please continue to follow our channel for more updates. Thank you for your support. Bye bye.